And we've met examples of both. Okay, so abelian means that the binary operation is commutative. Non-abelian means that the binary operation is not commutative. So let's just have some examples. So what about abelian groups? So there the binary operation has to be commutative. So lots of the ones we've written down. So any group of numbers that we've met is going to be abelian, either under addition or under multiplication. So those are all abelian groups. Lots more. What about non-abelian groups? Well, groups of matrices, so GLQ are, for instance, under matrix multiplication. That's non-abelian as soon as you get to 2 or more. 1 by 1 matrices, not particularly exciting, but 1 by 1 matrices are commutative under multiplication. But as soon as you get to 2 or more, it's non-abelian. We proved that multiplication of matrices wasn't commutative last week, I think, or the week before. But that example might not work here because we want to make sure that if we multiply two invertible matrices, it's not necessarily commutative. So just check this yourself. Find two invertible 2 by 2s that don't commute. Okay? So this is a very important non-abelian group. Let's take a natural number n, and this is another definition. I don't think I've actually defined this yet. I might have mentioned it in passing a couple of weeks ago. The symmetric group on n objects. So I've talked about symmetric groups in the first half. This is a symmetric group on n objects, or on n letters, is just the group of bijection of 1 up to n. So there are your n objects. You can call them 1, 2 up to n, or following one of the tutorials yesterday, you could name them after your favourite animals. But we've got n objects. We look at all bijections of that set onto itself. In other words, we look at all permutations of n objects. So you could think of them as letters if you want, and think about all permutations of those letters. We can compose two bijections. Again, another bijection. We've got an identity bijection, and every bijection has an inverse. So this is an example of the symmetric group from the first half. So this is the group, it's called the symmetric group on n objects. Well, the claim is that Sn is non-abelian for n bigger than or equal to 3. And I want to end today's lecture by proving this, and at the same time introducing some very important notation. So the claim is that as soon as n is bigger than or equal to 3, you've got 3 or more objects. This is going to be a non-abelian group. In fact, for n equals 1 and n equals 2, it is abelian. So these are very important non-abelian groups: the general linear group and the symmetric group. So, well, let's just look at n equals 3, because n equals 3 is actually enough, because as soon as you've done n equals 3, then any bigger n essentially relies on the proof for n equals 3. So we're looking at S3, which is a set of all bijections of 1, 2, 3 onto itself. It's a set of all permutations of 1, 2, 3. And we can write down all the elements. In fact, does anybody know how many elements there are? How many permutations are there of 3 objects? It is. It's 3 factorial equals 6. You'll be studying such things in such combinatorial issues in more detail next semester, but I guess you've probably all done some combinations and permutations perhaps before. Well, there's various ways of writing these functions. I'll use this notation. I'll use this notation for a minute and then I'll change to a more convenient notation. I'll put the numbers 1, 2, 3 along the top and then say where they go to. Well, one permutation is where I'll just leave them all where they were. That's the identity bijection. Or I could swap 1 and 2 around. Or I could swap 1 and 3 around. Or I could swap 2 and 3 around. And then there's 2 other ones where 1 goes to 2, 2 goes to 3 and 3 goes to 1, or 1 goes to 3, 2 goes to 1 and 3 goes to 2. So that's quite a clumsy way of writing them. So those are the 3 factorial equals 6 bijections or permutations of 1, 2, 3. If you like, the bottom row is the permutation. You can write 1, 2, 3 or 2, 1, 3, 3, 2, 1, 1, 3, 2, 2, 3, 1 and 3, 1, 2. But remember, these are functions. Well, here's the... and I'm just introducing this here, but we're going to get very good at using this notation by the end of the semester. Okay? This is called the cycle notation. So this is probably the first time you've met this cycle notation, so don't worry too much if it's not immediately obvious, but it's a very good notation. It's very nice to compute with. Let's look at this one here, 1, 2, 3 in brackets. I think Fraley actually puts commas in, or certainly one or two textbooks put commas in. I really don't like putting commas in. Just make sure there's a space between the numbers. Otherwise this might look like 12 or something, or 123. Just make sure there's a space between these numbers. Round brackets. If you put commas in, it then looks like an ordered triple, which it's not. What this notation means is 1 goes to 2, 2 goes to 3, and then 3 goes to 1. So there's a cyclic thing going on here. 1 goes to 2, 2 goes to 3, and 3 goes to 1, which is precisely that. 1 goes to 2, 2 goes to 3, and 3 goes to 1. So we're using less ink. So what about this one above it? That means 1 goes to 2, and 2 goes to 1, and 3 just goes to itself, which is indeed that one. And of course the identity, they all go to themselves. Okay, so this is what's called cycle notation. And in fact, for short, if we know that we're working with 3 objects, we'll often write, to save even more ink, 1, 2, 3, just as 1, 2, with the understanding that anything we don't write down is fixed. But 1, 2 really means 1, 2, 3. But anything we don't write down, we assume is fixed. You don't have to do that, but you save more ink that way. Of course, you need to know how many objects you're dealing with. You need to know the ones you haven't written down are fixed, so you do need to know which ones you haven't written down. So you can check that, for instance, if I look at 1, 2 composed with 2, 3, in other words, the second one and the fourth one, that's not the same as 2, 3 composed with 1, 2. So that composition, remember, means composition of functions. After a while, we'll even miss that out as well to save even more ink. For the moment, I'm just putting it in. So we're saying that the composition of 2, 3 with 1, 2 is not the same as a composition of 1, 2 with 2, 3. In other words, we can find two elements that don't commute in this group, so the group is not abelian. And I haven't really got time to check to do that now, but I advise you to check this. And you can check it using whichever notation you like, but I do want you to get familiar with using this cycle notation. We're going to have lots of practice at that. Okay? It's a very convenient notation, not just because it saves ink, but also because it shows underlying structure. Okay? But the message is, even if we haven't checked this yet, and I don't have time to do it now, since we can find two elements, 2 of the 6, that don't commute, then this group is not abelian. And in fact, the same will be true for n equals 4, n equals 5, and so on. So these symmetric groups are not abelian. They're very important examples of non-abelian groups. And they're the heart of symmetry. Okay, these symmetric groups are called symmetric groups because they're all about symmetry. We can't see that yet, but that's what they do. Okay, thank you very much